Good evening, and thank you for the invitation to speak here tonight. It's certainly a great honour for me to speak to you at this distinguished lecture. I don't know how distinguished I am, but certainly I would, I look forward to the opportunity to tell you a bit about the work that I've been doing over the last couple of decades. And it's obviously I'm not particularly gifted because I'm still working on music transcription after 25 years, so I haven't solved it yet. But maybe one of you can solve it for us and then I can retire. Okay, so having done that, to describe the work on transcription, I'd like to go on and look at a much harder problem, that is music understanding, and think about how transcription relates to how a machine can understand music, whatever that means. And I don't want to get into any philosophical debates about artificial intelligence and whether machines can really be intelligent or whether they can really understand music. I'm much more of a pragmatic person who just thinks if we can build useful tools that whether they are or aren't intelligent, it doesn't matter. As long as they appear to be and they do what we want them to do, we can be very happy with that. Okay, so let me work out what I'm doing with, where's my cursor? Oh yes, I'm over there, good. So, as an outline, I'm going to speak briefly about my background, just how I came to get into this field, because when I was young, it didn't really exist, and there's very few people in the world doing what we now call music information retrieval or music informatics. And so I kind of stumbled my way into it, and I'm going to talk about a few different methods that I've used for music transcription, and then the applications, as I said, to music understanding. And particularly one particular one I want to show you is some work on analysing melodic patterns in jazz improvisation. Okay, so my background, as Ichiro mentioned, I have a PhD in, well, he didn't mention this bit, I have a PhD in artificial intelligence, in logic, belief revision, if that means anything. Non-monotonic logic, it was kind of big when I did it, but nobody cares about it now. It's been replaced by neural networks. And I was always interested in music. I haven't played guitar most of my life. And I got the opportunity in 1999 to combine kind of these two halves of my life with the music side and the technical computer science, artificial intelligence, when I saw a job advertised in Vienna for a postdoc in AI and music. And it hadn't really clicked to me that these things belong together, that I should be combining both sides of my life. Because there wasn't much academic work in music technology. I mean, the music technology stuff was a different type of, it was how to use technology in composition or performance, but it wasn't about the type of analysis and analytical work like automatic transcription, the things I've been working on. So I managed to combine these interests, and I moved to Vienna and worked for 7 years and basically managed to establish myself as a researcher in this area, and then I got a faculty job in London at the Centre for Digital Music, where I've been now for just about 16 years. And I'm now the Deputy Director of the Centre for Digital Music, which is I think we've got about 100 people working in kind of the general kind of music technology area. And most of those people are, more than half of them certainly, are the PhD students in our doctoral training centre, which is on AI and music. If anyone's looking to do a PhD, we will be taking applications for next year, starting, so we'll be advertising in a couple of weeks' time, so look out for that. If anyone's looking for a faculty job, we need more faculty in our area, so please come and speak to me. Lots of things we'd like to do, and not enough people to do them. So, why work with music? Here I am standing in the whole of a music department, it doesn't really make sense to ask this question. I don't need to ask or justify my existence as a music something researcher. But when I write a grant proposal, it's always good practice, isn't it? Right? To think about this. Why work with music? We have to convince the rest of the world, even if we don't have to convince ourselves. And maybe some people here stumbled in accidentally and think, why does anyone work with music, and what are they doing with music technology? So I thought about, different reasons why music's important, and perhaps, I might be preaching to the converted here, but you can't put in a grant proposal that, I really love playing guitar, so give me £6 million for a research centre on AI and music. It doesn't really win the money. So firstly, music is immensely important in our culture, in all cultures, in fact. It's a universal. Every culture has some form of music. Now, certainly those forms of music are not easily comparable, right? They're extremely different. But music certainly exists across the world as kind of something that everyone relates to, enjoys, and it gets used in many different ways in our society. And I've listed some of them here. If you ask people have done these types of studies where they say, what do you use music for? What's its function? And people reply as the number one answer is for emotional regulation, which probably means it makes me feel good. Right? Or maybe they use it, I want to feel bad, I want to feel angry. I want something that wakes me up, gives me some energy to get going in the morning. So that's one of its functions, but it has another really important function, I think, and especially in these times of very divisive politics and a lot of people trying to get parts of society to kind of basically see other parts of society as their enemies. And music brings people together. It does the opposite, right? And historically it's been a really powerful force. When you think about it in the USA that people were playing jazz together, black and white people were playing jazz together long before they could sit together on a bus or go to the same universities, right? So it had a powerful force that it brought people together. I think it still does the same thing today. Of course, we use music. I mean, who would go to a party with no music? It'd be a very rare thing, right? We use it in our kind of recreation. Obviously, it's used from very kind of high and lofty things such as worship, but it's also used in advertising, right? It's used to get your attention. It's used to create something memorable which gets stuck in your brain, whether you like it or not. Sometimes it's good, sometimes it's bad. And so music has many functions. I think that's an important thing to understand. And then, of course, when you're talking to funding agencies, it's probably more useful just to skip to the next point and say, there's lots of money in music. And I mean, clearly there's always been a large music industry, and there's lots of money does go into music. It doesn't often go to the musicians, unfortunately, but somebody makes money out of it. And these days, what's changed during my career is that the music technology, the type of thing that I do, now there's a lot of industry involvement in that field. When I started, I remember meeting Roger Dannenberg in the 1990s and talking about, I mean, everyone who came up to Roger said, so how do you get money to do this type of work? Where do you get funding from? Because there was no industry in the area. Industry was fighting against technology in the 90s. They were doing everything they could to stop any technology from advancing in the music industry, right? Because all they saw it as was a threat, that people can copy digital music. Oh, dangerous thing. People will copy all the files and then they won't buy music anymore. So people were looking and asking, well, how do you get funding to do research? Because it didn't exist. Nowadays, it's kind of obvious. You just say, well, what type of work do you do? Music technology. It's like, oh yeah, like Apple, Spotify, and you can list 100 names like that. And lots of companies that didn't exist 10 years ago that are now worth more than more than you can imagine. So obviously there's a big industry there, but maybe the more important thing for me as an academic is that the academic side to it, the opportunity and the challenge. One side there's a challenge of how do we model human intelligence and creativity, which is a really important part of intelligence. So we're good at modeling kind of how people play chess and even language now we're starting to solve. But creativity is still a fair way off. And music's a really good field in which to study creativity. From a more kind of down-to-earth perspective, as an engineering point of view, that these kind of the complexity of the signals and the fact that music is multidimensional. It's not like speech where it's just one thing happening at a time. It's multiple different sources of sound playing together that make it very complex and kind of a technical challenge, at least, to analyse music. But it's an opportunity because we're living in the days of big data and big computers, lots of them. We can destroy the planet by using lots and lots of energy training large artificial intelligence models, right? So we have a problem there that we have to balance what we can do with what we should do. But there's an opportunity there to apply the technology, which is now incredibly powerful, to learn and understand things about important cultural artifacts such as music. And so that's what we're looking at. Okay, so that brings me to automatic music transcription, which I guess in the music department, you all know what music transcription is, as Ichiro said, okay, dictation, you might call it. But you hear some music and you write it down in some type of notation, something like down the bottom here, musical score. When we do it on a computer, we do it slightly differently. We would generally compute something like this time frequency representation. This is a spectrogram as an intermediate form, and then there we want to detect notes, and what we see here is on the horizontal axis is time, so this is time going from left to right, just like in music notation. From bottom to top is frequency, kind of like musical notation. But here we're talking about frequencies, so even if you play a single note, you don't just have one horizontal line here, but you have another one here. And these represent the partials in the harmonic series of the note. So if it's a pitched note, it'll have not just energy at one frequency, but at a whole lot of frequencies. And so usually the first step we want to do is condense those partials down to individual notes. And here we have what's called a piano roll representation. And so we want to basically detect where are the horizontal looking lines and where there's a whole set of parallel ones that start and end at the same times but are spaced evenly in frequency, which would be a harmonic series. And they would all get condensed down to single notes. That gives us our piano roll representation. And if you're an MIR researcher, you might stop at that point and say, well, that's solved. I found out when the notes, what pitch they have, when they start, when they end. That's all we need to know. We know what the musicians played. But of course, most of us are not very good at reading piano roll representations. And if you were given that to play, you might find it a bit difficult to sit down at your instrument and play it. So how do we go from there to the musical score? There's a huge amount of work involved in interpretation because we have to work out, firstly, what key are we in? What's the time signature? What's the tempo? Once we know those things, we can then start naming the pitches that we've recognised because we have to know, is it a C sharp or a D flat? We have to know, is this note on the beat or is it off the beat? Is it on the first beat of the bar or on the second? So we have to convert time in seconds to time in beats and measures and so on, and frequency in hertz, or it's been converted to MIDI pitch. But we have to represent that in musical units as sharps and flats and those types of things, and not just as MIDI note 61. Okay, so that's what the task is. Why is it difficult? Well, I like to make the comparison with speech recognition, because speech recognition is something which engineers have pretty much solved and have been working on for many decades, and huge amounts of money have gone into it and huge numbers of publications on the topic. But speech recognition is kind of easy. One person speaks at a time. Sometimes there's some background noise, maybe even a cocktail party. But still, you're focusing on one thing. In music, there's multiple simultaneous sources, and they're all important because they're all part of the music. So generally, we want to know not just what one person's saying at the cocktail party, but what everyone's saying at the same time. But unlike cocktail parties, where people tend to start and finish words at different times to each other, in music, the musicians rehearse so they all start and stop notes at the same time together. So there's not this kind of thing that one person starts a word, somebody else starts a word, somebody else starts a word, all at random times, and so there's no correlation, and that makes it easier to separate. In music, they all go together. They play a chord. It's like, well, how many notes was that? It sounded like one. They all blended together. Well, that's nice aesthetically, but it's actually technically a pain, because now it's hard to separate them again. So all of the things that work to make music sound pleasant to us also work to make it difficult to then pull apart and to recognize the constituent elements. And so we have this correlation in time. We also have a correlation in frequency, which I've drawn here on the diagram on the right. So there's a reasonably standard voicing of a C major chord, at least one that I would play on a guitar. If I was playing a bar chord, it would be exactly those notes. And I've marked the frequencies of all of the partials in the harmonic series up to however many frequencies fitted on the axis, up to 1,600 hertz. And what you see is that a lot of these frequencies overlap. They line up with each other. So when I play one C and I play another C an octave higher, in fact, all of the partials of the higher C align with partials of the lower one. They overlap. So in fact, there's no new frequency components, whether I play two Cs together or just the bottom one. The frequency components, which appear in the spectrum, are exactly the same. It's just that perhaps the even ones are a bit louder because you've played an extra note. But it's quite hard to separate these things unless there's some extra information we can use. And so music has these difficulties which make it, an extra challenge to separate. But that doesn't discourage us, because we all love music, right? So I'm going to talk about just a few different systems which I've worked on over the years. The first of these was my first PhD student, Matthias Mauch, who worked on chord transcription. So his goal in his PhD, which he succeeded at, was to create a system which could work out what chords were being played in a piece of pop music and basically output them. And it should be kind of in a similar way to the way a musician would write them out. So that's what we thought kind of intelligent was a word we used, but we thought, what does intelligent mean? Well, it means kind of like a musician. So it would do what we want it to do. And so what I've shown here at the top is just what you would buy if you went to your local music store and bought the book of some Queen songs. I think that's a line from a Queen song. This is the output from our system. The important part being this sequence of chord symbols. And the G, D over F sharp, E minor is exactly this line here. So it got that bit right. The notes underneath don't actually mean anything. They were just automatically generated from the chord symbols. Whoops. So our aim was to create this automatic transcription. And automatic transcription of chords is, on one side, an easier problem than the kind of the note transcription I was talking about, because you don't need to know every note that's played. You can work out the chords without actually working out every single note that's been played. But on the other hand, there's a much more difficult element to it, and that is the interpretative element. You have to work out which notes which have been played have a harmonic function, and which notes are just passing notes, or auxiliary notes, or whatever else you want to call them. Non-harmonic notes, right? Notes that don't belong to the harmony. How do you tell the difference? Well, if you know what chord it is, it's really easy, because if I say this is a C major chord and I play the notes C, D, E, F, G, then you know that the D and the F are passing notes. But if I said this is a D minor 7 chord and I play the notes C, D, E, F, G, A, B, C, then suddenly it's the E and the G which are passing notes and not the D and the F, right? So which comes first? It's a kind of a chicken and egg problem that there's no easy way. Now, of course, you can say, well, of course, it's the ones on the stronger metrical positions are more likely to be the chord notes. And yes, you can use those types of things to work it out. But there is this step of interpretation which isn't required when you're doing just note transcription in order to work out what the chords are. So the method we used was a statistical modelling approach called dynamic Bayesian networks. This is a type of hidden Markov model. I'll explain that a bit more on the next slide, where we try to integrate the musical context into the estimation of the chord, the idea being that it's not just kind of take a very small slice of audio and see which notes are played and then label that with a chord symbol. Right? There's a lot more that goes into it, because it depends what key you're in and what the previous chord was and all those types of things that will influence the way that it should be interpreted. So what we did was we calculated something like the time frequency representation I showed on a previous slide, the spectrogram. In this case, it was a log frequency spectrogram, because musical pitch is logarithmic in frequency. We tuned it to, because not everyone plays at A4 as 440 hertz when they record music, and even if they do, maybe when it gets transferred from the tape to the CD, then it gets transferred at the wrong rate or something, and it gets a bit sharp, a bit flat. So we tuned it so that these basically our frequency grid then lined up with semitones. And we also applied a beat tracker, and Itch was talking about that before, that I did this work on beat tracking. So we used a beat tracker to work out where the beats are in the music, and then just for each beat we calculated one chord, because chords don't change more than once per beat usually in pop music. Usually they stay the same for a few beats at least, if not many. So this is called beat synchronous features. So the features we calculated were for each beat in the music. And we had this approximate transcription method, which was actually a very simple, it was a built-in function in MATLAB, the language we were using, that gave us kind of an estimate of which notes were present. Basically that mapping from the frequency representation to the pitch representation on the previous slide. So, can I explain to you what a dynamic Bayesian network is? Well, probably not in the time we've got, but it's a type of hidden Markov model, which is a type of graphical model, where basically you have these variables which are described by circles, and you have arrows between them which represent dependencies between the variables. So if one of the variables has links to it from other variables, it says that that's dependent on these other variables. So depending on what those values the other variables have, that will influence the current one. And so in this work, we have 4 variables that we estimate. One is metrical position, one's key, one's chord, one's the bass note. And the other 2 variables here, the bass chroma and the treble chroma, are things which are derived from the audio signal. So this is the transcription step. Basically, we just kind of take the low pitch notes, go into the bass chroma, and chroma just means we throw away which octave it is. We want a pitch class and don't worry about the octave. So we have our observations for the model are this bass chroma and treble chroma, and the variables we want to infer are these four. And metrical position is very simple. It's a number from 1 to 4, because music goes 1, 2, 3, 4, 1, 2, 3, 4. Remember, we're counting in beats. Each observation is a beat. And we're dealing with pop music. It always goes to 4. It never goes to 3 or 6 or... Oh, it's a simplification, okay. It's a probabilistic model, so we have some very small probability that it doesn't do that. It does something else, but basically the assumption is nearly always right. It goes 1, 2, 3, 4. So we made lots of simplifying assumptions, but it was, an early attempt at this. The key, so we try to infer what key we're in, because that will influence which chords are played, and the bass notes we get from our observations. So if we look up here at this metrical position, so these, I should say, the two columns are time steps. So this is kind of the previous time step, what values these 6 variables had, and then this is the current time step. And so at the current time step, the metrical position depends on the previous metrical position. So if we were on the second beat on the previous step, we are now on the third beat of the bar. Very simple. And there's a very small probability that it could have jumped back to the first beat and started a new bar because it was a bar of 2/4 or something. As another example, let's say the chord, this is probably the most interesting one, is dependent on 3 things. It's dependent on the previous chord. Why? Because most of the time, the current chord will be the same as the previous one, because most chords last for more than 1 beat. Right? Very simple. It's also dependent on the key, because if the chord does change, it's likely to change to one which belongs to the present key. Right? So a diatonic chord is more likely than a chromatic one. And finally, the metrical position. Now, how on earth can the chord be dependent on the metrical position, you say? Well, do D minor 7 chords happen on the second beat of the bar? No, that's not the reason. The reason is because the chord is very likely to be the same as the previous chord, unless it's the first beat of the bar, where it's slightly less likely, because on the first beat of the bar, it's more likely chords change. So this is kind of the probability of the chord changing is influenced by the metrical position, not the actual chord itself, if that makes sense. So that type of intuition is built into this network, and it allows the network then to magically do its whatever Bayesian networks do. It does its reasoning and comes up with the most likely sequence of chords that explains the data that we've observed. Right, so we've observed, that's kind of the way these models work. They're generative models. So this is a kind of model that generates music, but we're not actually generating music, we're analysing it. So we run the model backwards, and we work out, well, which sequence of chords would be most likely to have generated the sequence of music that we had on our recording. And that's the way the models work. Okay, so that was our attempt at transcribing chords. And at its time, it was the best. We put it into the public evaluation, the MIRIX campaign, and it came out best for a year or two until somebody else took over, of course. My student graduated and somebody else was the best. But we enjoyed it while we could. So the second example I'd like to give of a transcription system is work that another PhD student did, Emmanuel Benetos. And this was based on the idea of non-negative matrix factorization, which is basically the idea that you can take the spectrogram, that time frequency representation, and you can factorize it into 2 different matrices, one which is kind of a dictionary of all the possible sounds which occur in this piece of music. When you think of piano music, this makes a lot of sense, right? Because there's only 88 keys you can press. And so there's 88 sounds you can make. And then the other, so you have, one is the kind of this dictionary of the 88 sounds you can make. And the other one is the activations, that is, when are those sounds made? And when they were made, how loud were they, basically, right? So they're kind of amplitude and time of the activations of what we call the templates, this dictionary of sounds. So you can think of it as, for piano, or you can think of the sounds as being your synthesizer, and the activations then as being your sequencer, telling the synthesizer when to produce which note. And that can be done for transcribing a single instrument or for many different instruments, because you could have your templates can be not just from a single instrument, we have many templates for one pitch for the different instruments, or for even different playing techniques on the same instrument and so on. The only kind of downside to this is as you add more and more different things that you want to, that you allow the system to use to describe the signal, what invariably happens is that although any one instrument played one note, it will try to explain the one note as being a combination of 5 different instruments playing that one note, all with different amplitudes, to get something closer to the timbre of that particular instance, because generally the timbres don't match, because, well, not every saxophone is the same as every other saxophone. Anyway, so this is the model, is that we're trying to do this factorization into templates and activations. And what we did in our work was we extended this model using firstly shift invariant, which means that we reuse templates across different pitches, because a C and a C sharp are very similar on the same instrument, except that they're, apart from the pitch, of course, but the timbre is very similar, so we don't need to have unique templates for every single pitch that can be played. We can just take a generic template and shift it in pitch. And that allows us not just to shift it by a semitone in pitch to go from a C to a C sharp, but also if we play the C with vibrato, or we do a pitch bend or whatever, we can also represent things between pitches. So that was something that hadn't been done in this type of work at the time. So we were looking at being able to transcribe music with vibrato and pitch bends, and this worked okay. And I can play an example of it, but I can't play it by clicking this because my computer doesn't allow that anymore. It says it's a security risk if I play files straight from my presentation. So I'll play it from here. So that's lyra music, if you've never heard of it, or lira, a Greek instrument. Looks, well, it's a bit like a violin, but they play it like this, kind of like a cello. And here's our transcription of the same music. Hopefully it sounds like it is the same piece of music at least. I'm sure it didn't get every note correct, but it sounds pretty awful because we're just synthesizing it on a MIDI synthesizer. But it captures the music. It worked reasonably well. And so that was one of the better techniques for transcription at the time. The next part of transcription I'd like to mention is some work we did. This is again with Matthias Malch after he'd finished his PhD and came back and worked for a couple of years with us. And this is work on a simplification of transcription to what should be really easy, and that is monophonic transcription, one note at a time. This should be solved, right? It's so easy. Commercial products do it. Oh, yeah, they do it pretty badly. So Yin was the kind of the state of the art in the world of speech recognition in the kind of the 2000s. And so we used it sometimes for some of the work we were doing, work on singing, and it was okay, but it wasn't quite there. So we looked at how we could improve it. And basically, there were two problems with Yin. One was that that it would, it relied on the choice of a threshold, which would often be, well, basically, it would work for, what works for one instrument wouldn't work for another one, or for one recording wouldn't work for another one. So you couldn't get reliable results out of it without a lot of hand holding, which is no good when you're doing big data type of work, the type of thing we were interested in. The other problem it had was it required post-processing. So the output it produced was reasonable. It would be, most of the time it got the correct pitch, but there were a lot of incorrect extra notes at transitions where notes begin and end, where there'd be just a 1 or 2 frames where it's an octave higher or an octave lower than it should be, or that type of thing. So we looked at how can we improve that, and we developed again a probabilistic model where we had basically introduced rather than just having a single threshold value, we'd say, well, we don't know what the correct threshold value is, but we know it's in this range, and it's basically defined a probability distribution for it. And then computed, based on that, the most likely sequence of pitches given this prior distribution of threshold values. And basically we're calculating then for all possible threshold values in this range, what would be the most likely output, the most likely sequence that would have produced the output we're observing. And it turned out that this gave us some really nice overall results. It was more robust and less sensitive to thresholds. So I'd like to give you a demo of it, if I can. Let's see, just to show you what it looks like. So we produced this system called Tony for analysing intonation. And I'm doing a live demo. This is really dangerous. This could fail. All right, so we load in a file of some random person singing. I won't tell you who it is, but it might have been one of the authors of the paper, and it's not me. Da, 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 da. Da, 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 da. So in the time it took me to load that up, it's loaded it, it's extracted the pitch track, shown in black, and it's put blue boxes around all of the notes. And you can just look at them and you see this note was sung with a frequency of 136.968 hertz. That's its median, because as you can see, when people sing, the pitch never stays fixed for any length of time. There's no such thing as beautiful horizontal lines as in piano music. Okay, so that's a really nice tool, and if it makes a mistake, such as it merges 2 notes together, you can just say, oh, that wasn't one note, that was 2 notes. Yes, split it into 2 notes. So you just can split it by, select edit first. And you split it into 2 notes somewhere in the middle. And then each of those notes then has its own median frequency and so on. Or if it's the other way around, you can merge them together. And if you want to extend them, if you say, this one wasn't long enough, you can extend it out, or you can say, no, that's too long. That bit at the end wasn't part of the note, and so on. So it's very easy to edit and fix things if you want to do analysis of the way people sing. So we did a couple of papers on how people sing out of tune, which was all lots of fun. So that's a system called Tony. I don't think I want to save it. So now we move on to the modern days, where suddenly everything we used to do gets thrown away, and now we just do everything with neural networks, right? So I had a student I think he joined in 2012 or 13, who was very eager to work with neural networks, and it was very brave in those days because none of the software worked. It was awful. You had to write everything yourself. Nowadays, you just use PyTorch or TensorFlow or these frameworks that just do everything for you. I think by the end of his PhD, he said that, I said, he got some really good results, and I said we should see if we can commercialize this or do something with it. And he said, no, throw it away. You could do this in a few weeks now with them. It's new software that's come out. Oh well. So what we did as our kind of first foray into working with neural networks was to follow basically the approach that's taken in speech recognition, and that is to divide the system into two parts, an acoustic model and a language model, where the acoustic model has the job on speech. It's the acoustic model kind of recognises what phonemes are produced, and then the language model chooses kind of sequences of phonemes that make sense, correcting the ones that, so that a likely sequence of words comes out. And this works really well in speech recognition, as anyone who uses Siri or whatever you use will know. So can you use the same approach for music? Well, the acoustic model is going to work out what pitches are played, and then the language model tells you what's likely to happen in music, which combinations of notes occur, which sequences of notes are likely to occur. This was very hard to learn, at least with the models that we were using. It gave us a very small improvement, maybe out of the results we have here, which were, we got great results in the sense that we were, at least 5%. In fact, these three results are all our work. There were three different models that we used. So the previous work, including my student, Emmanuel Benetos, improved it by about 10%. But only about 2% of that improvement was due to the language model. So there's very little help. Most of it was the acoustic model, and in fact, in further work that other people did building on this, they showed that they could do even better than we could with no language model, just by fine-tuning parameters and doing things that machine learning engineers do. The other thing that's interesting in these results is that the drop in performance when you go from the same piano to a different piano. So this means that the neural network has been trained on other recordings from exactly the same piano in the same room, same recording conditions. So it knows what that piano sounds like. It knows what a middle C played on that particular piano sounds like. And so it can recognise them very easily. And if you play one on a different piano in a different room, suddenly performance is 10% worse. Right? That's a huge drop. But I've seen it consistently in all types of work that we've done, that when you go from kind of training on known instrument sounds to unknown ones, in this case going from synthetic to real acoustic pianos, right? And piano synthesizers sound pretty good, right? They're not that different, are they? If you're a computer, they are. So there's a big gap there if you want your system to work on any recording from anywhere, right? On the other hand, if you're working with, a particular, you're working on concerts that happen in this hall on this piano, then you can tune your system to work really well for this piano, and it will. And I fear that a lot of the brilliant results we're seeing in music transcription are in fact more of an effect of the fact that they're often learning on just one piano. And of course, it's getting really good results, but it's not going to work well in the real world. So quickly, two things that I've had absolutely no involvement in at all, but I wanted to mention them because they're the next steps in music transcription. And they've come from industry, basically, Google. So once Google sends you an email and they say, we just saw your paper, we found it really interesting, you think, oh, great. And then they say, and we're going to re-implement it and do something better. You go, oh no, they've got more resources, they've got more data, they've more computers. I can't compete. I've got no chance. So I should have retired at that point. But they didn't offer me a job. Oh well. So they came up with a system which is not too surprising in the sense that, it's still got this convolutional thing which is doing the what we would call the acoustic model, and then the recurrent part of the network, the LSTM part, is a bit like the language model. It's doing the smoothing. But the really clever part about it was that they did this multitask thing where they said, we don't just want to learn what notes are being played, we want to know when are the onsets of new notes. And we're going to train this as an onset detector as well as training it as a transcriber. And then the transcriber isn't allowed to have any new notes unless the onset detector says there was a new note at exactly this time. And so by training these two tasks at once, because onset detection works quite well, a lot more reliably than our transcription systems. So by doing that, they were able to kind of link these two things together and produce a system which was a lot better than what we had done not many years before that. And then Chu-Chang Kong, who's at ByteDance, although this work was really done at Surrey University when he was a PhD student, took it one step further, I think, and he wanted to very precisely estimate not just the rough onset time, but the exact onset time. So even if you're calculating frames of data and you want to find kind of the frame, which frame did this note start in? Now he says, no, I don't want to know what frame. I want to know how far between this frame and the previous frame was it? Exactly where did it start in milliseconds? Okay, and he also wanted to measure the pedaling and the velocities, and he put together a system which is more complex because it's now got 4 different neural networks, all working to calculate their own part of the equation, the onset times, the offset times, which pitches are present in a frame, and the dynamics or velocity in MIDI terms. And if you remember the results I was getting, 74% 5 years previous to this, 96.7. But this is on Maestro, and this is one piano. So I say I don't trust it. In the real world, it's not as good as that. Google's one, 94.8. So you managed to outdo Google, which is always an achievement. But that's kind of the state of the art in piano transcription. The last thing I wanted to talk about in terms of transcription is work that a recently graduated student of mine did on lyrics transcription. So this is a totally different thing. Rather than worrying about what notes have been played, what about what words have been sung? You say, well, just use Siri. That works perfectly, right? Try singing into it. Somehow, when people sing, suddenly they pronounce words very differently. They pronounce words much longer than they would otherwise. They also have all these instruments getting in the way, making noises that sound like consonants, right? Those snare drums and cymbals and things. And so any system you try on it just doesn't work. So we developed an approach using what is kind of considered old-fashioned, these hybrid DNN, HMM architecture, because these days everyone wants to do end-to-end deep learning systems. But CalD is this framework which has been around for many years and is still used a lot in industry. It's a real pain to learn, but once you've learned it, it's incredibly powerful. And so we were able to train our model, again, acoustic model, language model, this is how stuff is done in speech. And we developed our own network, so we tried some tweaks on kind of the networks, the state of the art that existed, and found some ways that worked slightly better. Language model, very important. People don't sing the same types of things that they say, right? That shooby-doo-wop doesn't appear in speech. I just said it. I love you. Doesn't really, we just don't do that in speech, but it comes up all the time in singing. And so you need to train a system on, it needs to know that this is a different type of English language or whatever language you're going to train. And so we did some tricks to take the kind of the standard pronunciation dictionary that's used for speech to allow things like vowels which are 10 times longer than they are in speech. And we trained the system both on accompanied and unaccompanied singing and put in some tricks for it to recognise the singing well, when there isn't singing, because it's not just silence, because it could be accompaniment. And we found that we could get, these are error rates, word error rates. We found that on the unaccompanied singing, we weren't doing much better than what other people had done. But on singing, on accompanied music, we found the error rate was, we could get much, much lower with this system. So that's gone into a product, Score Cloud Songwriter, which is, I was very impressed with my student who, to have something that went into a product while he was still a student, that's already on the market. So that's work on transcription. So I want to briefly talk about kind of the application of what we do once you've got a transcription. Why is this important for music understanding? And I'll just talk about one project I've worked on. And that is it was a Dig Into Data Challenge project. So that was one that involved US and French and German and UK partners to look at melodic patterns in jazz. And the basic idea was that we can do a lot now with our powerful computer models, access to lots of data. And so we kind of know, everyone knows that when musicians improvise, they use patterns. That's what they spend all their time doing, practicing patterns, right? They get the Bebop Bible or the Charlie Parker Omnibook and they just practice and practice and practice and they can play them all fast, right, in every key, in every position, whatever, and then they go out and perform them. But how do these patterns vary, evolve and spread? Can we analyse that? Can we track them as they spread around the world? Somebody must play a pattern first and then other people copy it, right? And then how do you measure how influential a musician is? Well, by how often their patterns are copied, just like we do with researchers, right? H-index, right? You look at how often is this person's work being cited by other people. So we wanted to look into this question from a very computational perspective. Of course, we were grounded by having some real musicologists in the group, in the team we worked with. And so we did this work on first extracting the solo line using transcription technology. Similar to the other ones we looked at, it had a convolutional network and a recurrent part for the kind of the language model part. And we expressed the patterns then as melodic patterns, just basically sequences of pitch. And then we used the edit distance, or Levenstein distance, to test how similar two sets of patterns are. And then, we think this is kind of useful, that if you can understand the patterns, then you can recommend music to people, use it in teaching people about music, and also if you want to generate music automatically. So I'd like to show you an example. Let me just get this right. So this is one where it's much easier to explain what we did by showing you the output of our work. We have this website, I should say, connected to our database of patterns that we've extracted from solos. And you can play with this. It's open. It's there for the whole world. You type in a pattern, and we're expressing these patterns as patterns of intervals. So 2 means go up 2 semitones. -3 means go down 3 semitones. So you give a list of these numbers, and you search for it, and you get a list of hits. And if you're lucky, these will include the score, but they'll always include the musician, the track it's on, the year, start time in the track, and so on. But the interesting thing is, of course, that you want to listen to it because this is music, right? Right, and you know there's a YouTube video of 91 of these, or however many instances of the lick, right? So you can think of any pattern you like, type it in. Has anyone played this before? Or you play your own patterns and see how creative are you really? Do you play the same things all the time? Right? If you're a jazz player, that's kind of the thing you worry about as you go to sleep. It's like, am I being creative or am I just playing the same things every night? Well, now we can analyse it and work it out. So that's work that we've done looking into kind of patterns, and that's the point here is that, you know, the music transcription is just a tool to get us to a point where we can extract this information so that then we can do something interesting musically to understand, you know, what people do when they play music. So we can display this information on a timeline. You can see all the different people in the database who have played this same pattern and when they played it. We can do networks of people who played it and kind of, you know, look at who's similar to who. So some of these patterns, this is, that shows kind of, you know, a whole lot of different people playing the patterns. So other work that we're doing that uses transcription in my lab is, I have one student, Huan Zhang, who's just been going for about a year, and she's looking into expression in classical piano performance. And to do that, she's transcribed tons and tons of piano music using these models that I described today. And looking to extract kind of, you know, what are the expressive things that musicians always do? What are expressive things that only Glenn Gould does, or that only whoever the other famous players are? On the other hand, I have a student working on jazz, Dave Foster. He's not a sax player, but he's a bass player. But he decided he was interested in looking at expression in jazz saxophone performance. He recorded 24 hours of saxophone music, transcribed it all using tools, but checked everything by hand. He has 2,000 pages of transcriptions, and he did it in maybe 6 months or something, which is like, I think most of us would take 10 years to do that. Amazing guy, like really. This is an example. I mean, maybe there's a mistake, but it's great. So this is a database, and this has many possibilities of what you can do with it, because once you've got the audio and the transcriptions and the mapping between them, then you can teach a computer to do this for you next time. And I have another student, Drew, who's just been going for a year, and he's looking at jazz improvisation solo piano. So again, using those solo piano models, which work so well. And he's collected a huge database of recordings to then analyse and to create kind of generative models of jazz performance. They don't sound great yet, but he's still got a few years to go. So, probably data is the thing which limits what we can do. We have incredibly powerful machine learning models that really, you know, they kind of work well for the tasks they're given, right? For the things they've been shown lots of data. So the piano transcription stuff works really well because there's tons of piano data to train it on. Whereas other things, until Dave's data set, we didn't have hours and hours and hours of saxophone music with transcriptions that we could train a transcription model, but now we do, so we can do it. So just for fun, one of my students took Dave's data set and built a saxophone separator, so it separates the accompaniment from the sax playing, and this is what it sounds like. This is just taking a random sax track off YouTube, so this is with accompaniment, and I think it's Sunny Stit. almost perfect. Every now and then you'll hear a little bit of accompaniment in the background, but basically. So data gives us the power to do that. I can't do that for trumpet, because I don't have 24 hours of trumpet music with separated from the backing. So once we have the data, we have the ability to model musical phenomena, and I think that's the exciting position we are at right now, and I think that's something I'm going to be doing for the next few years of my research career. And so thank you very much for your attention, and I should say thank you to all of my collaborators who contributed to this work, which I've described. They did the work. I was kind of, supervising it and, nodding at the right times. And of course the funding agencies, which made it all possible. So thank you very much.